Then let's take a look at what we have for the first part. Before we go into the programming, let's look at what we want to program. So typically we come from some mathematics and we take this mathematics and bring that into a MATLAB script. So we're going to do that as well, and to get used to it, our mathematics is very simple. It's the example taken from the materials. So this is an equation. The equation shows how to calculate the volume when it is a volume that is not constant, but a volume that changes over time. It means we are looking at a dynamical system. So for this volume, we have a formula, an instruction how to calculate this formula, and this instruction notably contains time as a variable, as something that changes. It's an independent variable because time changes whether we like it or not. So time is represented by the letter t here in our equation, and we can see it's at the very end of the model. And because we just have something multiplied with time, no power or square root or logarithm of the time, this model of the volume is linear in time, as we say. So time taken to the power of 1, which of course we don't write because it's trivial. What else do we have? We have then two constants that we need to know in order to calculate the volume. One constant is the so-called growth rate. This is a constant that is multiplied with the current time, and it has units of difference in volume divided by unit time. So you have that at the bottom here. So difference in volume is the change of volume per unit time. How much does the volume change per second, per minute, or whatever you want? In this case, we have per minutes, because we're going to look at processes that are supposed to happen in terms of minutes. So this is one of our constants that we need to specify with its corresponding units, say cubic micrometers per minute if we think of bacterial volumes modeled here. Our second constant, the initial volume, is something that we need as a constant to start with, where we can say this is our starting point. We can define a time that is equal to 0, the start of our process or of our observation. And at that time, when the second term is not there, then the only thing left is the initial volume. What volume do you start with? So this is just a constant offset, as we say. Taken together, the two terms sum up and add to the volume. So all of this is going to altogether have units of, in this case, cubic micrometers. So this is our formula. We have it explicitly with constants given as 0.4 for initial volume and 0.02 for growth rate. And what we want to do is we want to see this now executed and visualized in MATLAB. And this is where Rob comes into the game, and we'll see how to do that.
Okay, so let's get MATLAB open. So today we're going to do everything in script files. So I'm going to open a new script. And of course, to run a script, I need to save this onto the desktop. Well, I can save it anywhere. I'm going to save it onto the desktop. So I'm going to save this as linear growth. Of course, you can save it as whatever you like, as long as you remember which file's which. And then in order to remind us what we're doing, I'm going to start with some headings, linear growth. And because we don't want this file sitting here all the time, I'm going to remind us what the function we're going to be working with is. So it's v equals 0.4 plus 0.02 times by t. Okay. So now I can hide this for the moment. Bring up the MATLAB main window so we can see the output of our script file in a minute. Okay. Of course, save this. Okay, so we're working on this linear growth. Today we're going to use, inside our scripts, we're going to use things called anonymous functions. So anonymous functions are one-line functions where we don't need a separate file, but we can do them in one line. We can define them inside our script. So we have the initial volume and the growth rate. So 0.4 is the initial volume and 0.02 is the growth rate. So first of all, we need to define the anonymous function. Helps if I spell anonymous right. Okay, we do this by setting it to a variable name. So in this case, we're going to have a function called lin growth. Okay, so exactly like we'd set a normal variable to a name, so lin growth, we're going to set a function to that name. The syntax is slightly different from other things we've seen before. We need an @ sign, and that tells MATLAB we're looking at an anonymous function, and brackets. Inside those brackets, we put the inputs to the function. In this case, we've got t. After the brackets, we can write the, in this case, the mathematical function that we're interested in. So 0.4 plus 0.02 times by t. Okay. So this whole line now defines a function called lin growth, which takes one input t and outputs the result of this mathematical expression. So if I save this, run this script to get this anonymous function into the memory, I could just run lin growth 1. So after one time step, after t equals 1 minute, what's the output? Oh, it's 0.42. And we can see 0.4 plus 0.02 is equal to 0.42. Okay? But what we want to do is plot this function. Is say if we've got a range of time between 0 and 20, in this case limit equals 0 to 20, then we want to plot this function between time point 0 and time point 20. Well, MATLAB has a really useful function called fplot. This takes two arguments. It takes the function name and it takes the limits, so the min and the first time point to the last time point. Of course, it's always good to label our axes. So that we know what we're talking about. Okay. So let's see if we run this now, what happens. Save it first. Okay, so what we're getting here, so from an initial volume at time 0, 0.4, which is what we had before, we're growing linearly. So after 20 minutes, we've got a volume of 0.8. Is that what we expect, Gerald?
Yes, this is what we expect. And it brings us to the fact that we can use any function with a single variable, which is time in our case. We are able to, just by this definition, we can put it into a graph. And we can look at all of its features like starting point, ending point, and so on. So the one thing that concerns us a little bit here as from a programming point of view is that with these very specific values of 0.02 and 0.4, everything is of course very specifically designed for exactly one process. So typically in modeling, we want to have things set up a little bit more generally, such that we put in the parameters, and if we specify the parameter then for different processes, that we can adjust them individually. So let's assume we have different populations where the volume grows differently, and then we would have different numbers, say, for the growth rate. It could be 0.03 or 0.07 or things like that. So the question is, how would we go about in MATLAB if we wanted to have a generic parameter where we only need to change the parameter and still have the function plotted in each case for the different values of that parameter?
Okay, so should we pick just one of these to change for now? We could obviously set both the initial volume and the growth rate as
Well,
variables.
let's start with one maybe. Pick one, maybe the growth rate.
Okay.
And we'll leave it for the audience to do then the exercise and also turn the initial volume into a generic parameter rather than this 0.4 value.
Okay. So in our lin growth anonymous function, previously we had 0.02, and we're going to change that to a new variable called g rate. Okay. But previously we've said this at sign and the brackets have all the variables in the function, but now they don't. Now it's got both t and g rate. So we need to add g rate into this set of brackets. So now lin growth will define a function of both t and g rate that gives us the value of this mathematical expression. So anything that we have in here that we haven't otherwise defined, say it's a function of x and y, we need to have x and y inside the bracket that is prepended by an @ sign. Okay, and this is all called an anonymous function, so if you have any trouble, just Google MATLAB anonymous function or ask on our forums. So unfortunately what's happening now is that fplot expects to get just one thing, x, but t, but we also need to set g rate. So if I try and run this, we'll get an error. So error using our function as defined in the text, so lin growth, not enough input arguments. So that means fplot doesn't know about our second argument and so doesn't know to set it. So we have to do a little bit of a modification to our later code. I'm just going to close the previous plot. So now instead of just giving it lin growth, we actually need to define another function that uses lin growth. So I'm going to do another anonymous function. And now I'm going to call lin growth. And so we still want t, and we still know t is going to be used by fplot, but we need to set growth rate. So what I'm doing here is taking the initial lin growth and putting it inside another anonymous function that only has one input argument, and the other one is defined inside the definition of the anonymous function. Okay? It's a little bit complicated, but basically fplot expects functions that only have one input argument. So now if we run this, we get our plot as expected.
So we're getting the same thing as before, because now you have told in the second line, the new line that you added, that growth rate is going to be 0.02. So it's defined as before, but in another location. And it's of course important to keep track where this location is exactly going to be. And we can see from the definition of lin growth in line number 5 of this piece of code that it's going to follow after t. So you can now try to experiment with this and also set the initial volume into a name. May call it something, and then replace it, and then add it as yet another modifiable quantity that follows, for example, after the growth rate. So growth rate, comma, initial volume would be a way of introducing two such parameters numerically.
So that would be in this initial definition of the first anonymous function. Of course, then you'd also have to set it inside your second anonymous function.
And then you have to give this number as well at some point later on in that area highlighted yellow in this moment.
Okay.
Right, that concludes our initial exercise. And so we have seen a function, and we have seen how it's a function that relates to a description of a biological process. And we have also seen how the function definition within MATLAB combined with fplot is a way to help display the function in periods of time that we would like to see.